All right, welcome everybody to chapter 3. So this chapter is now sort of the first more technical chapter. We started with an overview of what is machine learning. We took a look at the entire machine learning life cycle. These are very important processes, important skills, and we'll see how fast we get through the technical content of this chapter. Um, and if we do get through and have a little time at the end, I think we can also talk a little bit about how the things discussed here also reflect in it, because ultimately it's some of these skills around decision making. Should I stop here and say that this is my final model, this is really good, or should I keep going? And if I'm going to keep going, then what do? Do I work on the data? Do I try to find a different algorithm? Do I try and hyperparameter it, right? So these are the kinds of things that ultimately are, in my opinion, the skills that separate an experienced data scientist from a junior entry level machine learning engineer. All right. So can I please Zoom have you go away? Thank you. All right. So the chapter starts, it shows us the MNIST problem. This is a very common problem that is an example problem for learning. So we have these grayscale images of handwritten digits. The images are 28 by 28, so relatively small in the grand scheme of things, and that makes it easier for us to work with the data in terms of how long it takes things to train. It also allows us to do demonstrations with algorithms that are not super powerful, and that's sort of the point of this chapter, is not to talk about all the algorithms, but rather to talk just about what is classification and how do we measure it. All right. So after introducing this MNIST problem and showing you that it's small enough, it's easy enough that there's places where it's just available, you can download it. Then there's the section training a binary classifier. So I have a couple notes here. The author uses an SGD classifier. All right. And I don't know, honestly, that I use the SGD classifier at all. But it is a reasonable starting point, in the sense that this is a linear model. It's pretty basic. Okay. It's a good baseline starting point. If the SGD classifier can't solve your problem, that doesn't mean that you should stop, because it's a very basic one. But for simpler problems like MNIST, it'll actually be able to make some progress. You won't get anything that's like close to random. You'll actually get some reasonable results. Um, so I, so the author doesn't explain what the heck an SGD classifier is, but basically it's a linear model. So if you're familiar with logistic regression, it's pretty close to logistic regression. Okay. Um, and the way it is trained, as the SGD at the beginning, for those who know, what that means is it's trained with stochastic gradient descent. All right. We're going to learn more about that later, but the main thing is that it starts with some randomly initialized parameters, it guesses, and then it basically just looks to see in which direction would it get a slightly better answer. Should I tweak this number up a little? Should I tweak this number down a little bit? And it does that. And if you're familiar with loss functions, then what it's going to do is it's going to find a local minimum. So where the loss is the lowest in that region. There's no guarantee that that's the global minimum. Okay. But the nice thing about this SGD classifier is that it'll pretty much work on anything. So it may give you a bad local minimum that's not the global, but it won't actually error out. It won't fail to learn or whatever. It'll find something for you. Okay. So I think that's a pretty good example of something to start with. Um, and like I said, it in the second bullet here is, it doesn't really have very many assumptions about your data. So the assumptions about your data, if they're right, can give you a very powerful model. But if you have assumptions about the data and they're wrong, then it can lead you astray. So so that was my additional comment in terms of SGD classifier. one of the things we'll see in this book is that it's kind of meant to be an overview of what you can do with scikit-learn, and then later with Keras and TensorFlow, and the new edition that's supposed to come out within a few months, they swapped out TensorFlow, and they were the authors replacing it with PyTorch. I didn't know that when we started, but yeah, people have told me that there's the new edition that's coming out. So I bring this up just because you should know there are some things that are used more often in scikit-learn, and there's some things that are used less often. And the author's going to try to kind of do coverage of everything that's in scikit-learn. And so it might seem like everything's equally important, but they're not all equally important. Okay. All right. So then the heart of this this chapter gets into the performance measures. So the author, they have their SGD classifier, and then he says, hey, we're going to use 3 folds. And instead of having like 80% of the data for training and 20% for validation, by using cross validation, he gets to use all of the data. I think it was like 60,000 trained, 10,000 tests. So he gets to use all 60,000. Otherwise, if he had split it 80-20, he would have, what is that, 48,000 that he trained on and, 12 on the side. But I did want to note that I think I might have also noted this last week. When you do k-fold cross validation for real, people pretty much always do either 5 folds or 10 folds. So is anybody here familiar with like where this 5 and 10 business comes from, or what the intuition around this is? So there was a research paper. I'd have to Google it to find it. It's many, many years ago, probably over 20, maybe over 30 years ago. But the basic gist of it is, let's say you did just 2 folds. Okay. The whole purpose of k-fold cross validation is that you're doing multiple folds and you're getting multiple data points, and that's giving you a more accurate validation score than if you just did one holdout validation set. If you only did 2 folds, you haven't really changed that much from doing just a fixed split with only 1 fold. Not only that, but your folds are half-half. So you're training on half the data, you're validating on half the data. And that's a lot of validation data. So your training set gets a lot smaller. So for that purpose, it's not so great to have K be really tiny. So for 2 and 3, you're losing a lot of data to validation, and you're not getting as many data points. And so at some point, things get a little better. And what was demonstrated was that around 5, you have this really nice point where now you've got 5 different data points in terms of estimating your validation error. And you're only using 20% of the data for validation. So you're still training on 80%, a decent chunk. If you go to 6 or 7, it's not that different from 5. You don't get much benefit, but 7 takes like 40% longer to train because you have to train it 7 times instead of 5 times. But every now and then you really do want to do a lot. And so sometimes you'll see people do 10-fold cross validation. And that means that in every one of the 10 runs, 10% of your data is being used for validation. So again, you're getting more of your data, you're getting 90% for training on each of them. But it takes twice as long to train as 5-fold cross validation because you have to do it 10 times. So anyway, that's sort of the intuition, the background behind the number of folds. And so generally what you'll see is people will do 5-fold cross validation. 10 is rare, again, just because it's so much slower. And early on when you're experimenting, one of the things that Ryan mentioned last week, if you guys recall, is you can set up 5-fold cross validation and you can actually just break out of your for loop after the first fold. All right. And that basically is just doing an 80-20 split, a fixed split. But you have all the code there. And as soon as you comment out, that break, then you can actually have it do all 5 folds and average them. So that's a way in which you can sort of set up your code to do the best of both worlds, But if you don't want to wait for it to train 5 times, you can just iterate a lot faster. And so yeah, so a common thing you might do is set up cross validation, run it, and print out the individual validation errors from all 5 of your folds. And if they're very similar, then you're pretty safe at that point, just using one for a long time till you get close to the very end, in which case you want to be more precise. But if you're just at the stage where you're like, well, I don't know, would a decision tree do better than my linear model? One fold's usually probably enough at that stage of the game. All right. And so then my second note is, which relates to the thing I was just saying about having your own for loop and doing things, is from what I've seen from people, it's relatively common to use Scikit-Learn to create your folds, your 5 folds, but then do your own for loop and do your own thing. Just because it allows you to do stuff like I can stop it after the first loop, and I can have custom code in there. So the built-in, cross val score, cross val predict, these are really great and really convenient. But let's say you just wanted to calculate an additional second metric for some reason, or you wanted to do some visualization and you wanted to, whatever, display some kind of chart or something like that. It's really trivial if you have your own for loop to just slap it in there. And it is possible to do these things with Scikit-Learn with these built-ins, but it's just a little bit more obvious if you have your own for loop. And so I think that's pretty common. You see people use Scikit-Learn to set up the folds. It'll build all your indices, and then they just manually do the iteration themselves. All right. I said quite a bit about that. Any questions about the cross-validation? I'm not sure if I understood the question. You're asking if we do 5 folds, am I expecting potentially different answers for the 5 folds? Yeah. So the if your data is very uniformly distributed, and especially if you have a lot of data, what tends to happen is you get almost identical results from each of the 5 folds. And so under those circumstances, you're pretty safe for the purpose of speed, just using one fold and reading that number as if it were the average of all 5, even though it's not. Okay. If you have a small amount of data, or sometimes if you have data that has kind of some extreme values, some outliers. Okay. So if you were, I don't know. I'm trying to think, like, if you had some kind of customer behavior or whatever that you were predicting, and you had like one customer who was a whale and like just spent 10 times as much as any other customer, whatever they're in, if they're in your training, that's going to pull your training up in a way that's not representative of the other 99% of your customers. And if they're in your validation, you're going to get them wrong because you just can't possibly predict that one guy that's, and so you can run into bad luck issues either way that person falls. But if you do 5-fold cross validation, then they're going to be in validation once and they're going to be in training 4 times. And then when you average those, you actually get a more realistic estimate of how your overall performance is. And so that would be a case where just taking one fold might not be a good idea. But for many, many problems, you have enough data and the 5 folds look pretty similar. And you're like, okay, to get a really good answer, I need that. But early on, if I can improve if my folds differ by 1%, okay, and I'm at 65%, then if I try a new architecture and it gets me to 68, then I don't really need to know whether I was at 65 or 64 or 66, because 68 is better than all of them. So that's the kind of the general idea here. In the chat, somebody asked, is above 10-fold not recommended? It's not a bad thing to do more than 10 in that it's not going to cause any problems. Okay. Um, all it's going to do, though, is it's going to make your training more expensive without necessarily any benefit in terms of having a more accurate understanding of what your validation error is. There is a form of cross validation that's extreme. That's called leave one out cross validation. And so for that, if you had 500 data points, you train the model 500 times, and each time you just leave out one sample as the validation set. Now, that individual validation error is completely not useful because it's just based on one sample. But now you're going to have 500 of them that you average. And leave one out cross validation is extremely accurate. But if you have 500 data points, you have to train your model 500 times, which is why generally people don't do it. And I think it's not even mentioned. I think it might have been mentioned in an earlier edition of the book, but the reality is our data sets keep getting bigger. And you know, if you have 25,000 data points, you're not going to train the model 25,000 times. It doesn't matter how fast it is. You know, do the math. If it takes 1 second to train it 25,000 times, you know, but statistically, you know, that is something. So there is no overfitting problem. It's not a bad thing from a measurement perspective. It's just a bad thing from a time and computing costs. Yeah, question, please. I mean, mathematically, yes, yes, you can. Well, the thing is, whatever k is, if you say fivefold, tenfold, 20-fold, that's how many times you're training your model. So that's where when I say 10 takes twice as long as five, it may not be exactly because each of the 10 may take slightly more, slightly less than the five. As you go to higher folds, you are using slightly less data for validation and slightly more for training. So in theory, if anything, each run is going to take a tiny bit longer. So I would expect that tenfold generally will be a teensy bit more than double. It will be double. There will be no diminishing point or whatever. And so 20-fold, you're not talking about 4 times as long as fivefold. And if you did 500, then I expect it to take 100 times as long as fivefold. So that's the reason why people don't do that. Yeah, there's not a reason to try different folds in terms of like it makes your model better or different. What it really is about is you want an accurate estimate of your error, of your validation error, so that when you make changes, you can see if there's improvement. Okay. So if I'm building my house price prediction model and I do fivefold cross validation and I see that the 5 different folds have very, very different errors. You know, $5,000 off on the price of the house, 25,000 off on the price of the house, 10,000 off on the price of the house. Then if I train a new model where I say, oh, I'm going to add a new data point that says, does this house have, I don't know, nice cabinets in the kitchen? Okay. And if my error reported to me is less by 500, I don't really know if that's a better model or not. Was that just noise? Was that just luck? Because I'm seeing these wild variations, 25,000, 5,000, whatever. So what you really want is to have as accurate of an estimate of your validation error. And if doing more folds gets you a very consistent, the individual folds may vary, but a very consistent average, then you may be able to see, a $500 or $700 improvement is a real improvement. It's a slight improvement in the right direction. And so that's really the idea here is, can you tell the difference between oh, I trained this model with a different random number seed and it was 500 better. That's not actually a better model. That's just luck versus I did something and it really is moving in an uphill direction. There was also a question in here about nested cross validation. And the idea for nested cross validation is the way I think of it is really just if you have two different things that you want to test simultaneously, um, then basically what you can do is you can test one of them the normal way with cross validation, and then you just stick another for loop outside that where you test the other thing with cross validation. Okay. Um, if you didn't do it that way, then say if for the second thing you only ran it once, well, then you're not necessarily getting a very accurate estimate of your error. So it's a useful thing, and I think it's important to understand just this general principle. Do I have an accurate estimate of my error? If you have an accurate estimate, you may not necessarily need to use cross validation at all. So if you're like, hey, I'm trying to do cats versus dogs, and I have a million images, and so I reserved, you know, 1% of that million images, which is still 10,000 images for my validation set, you probably do not need cross validation because you have such a large validation set that if it says you're 87.2% accurate telling cats from dogs, that's probably right. When you have really small data sets, then you really, really need to worry about, oh my gosh, I have a validation error number. It's a floating point number. Python is going to print out that it's 76.1234567 8, but not all of those digits actually, mean something, right? So it's really just about to what degree is it whatever I said, 76.1234 plus or minus 0.001, or is it 76.1234 plus or minus 7, in which case you don't even need the decimal points, right? So that's the idea here, is cross validation is really your best friend for checking to see if you have an accurate validation error, and it's expensive. So that's the real trade-off here. I don't do it all the time because it's 5 times as expensive. If I had all the time in the world, I would. I would always, always, always use cross validation. Okay. Uh, moving on to the confusion matrices. So I could be wrong, but as far as I know, confusion matrices, you have rows and columns. And for binary classification, it's a 2 by 2. It's just 2 rows, 2 columns. Okay. And one of them, either the rows or the columns, represents the ground truth. Is this really class, one, a positive or a negative? And there is no complete standard as to whether the ground truth should be in the rows or the ground truth should be in the columns. I'm sure one of them is more common than the other. But if you just see a confusion matrix and it's not labeled, then you should ask. You should not just assume that one is the predictions and the other is. And I think it's pretty hilarious that I've seen confusion matrices where they actually have labels and it'll say like T and F, true and false, or whatever for the columns, and T and F for the rows, but it won't actually label beyond that which is the ground truth and which is the predictions. So at least you know that the correct answers are on the diagonal, but as to whether it's a false positive or false negative. So I just wanted to mention, beware. You just have to ask. Um, the other thing I'll say is that I look at these things and I see these formulas, and I actually understand. I've done it enough that I'm quite comfortable with what is precision, what is recall, and then I'll see a formula for precision, and it'll say it's whatever TP over something, TP plus FN FP or whatever, and like I don't know, maybe it's just I have a mental block, but it'll take me like 3 minutes to look at the formula and confirm. Wait, is this false? That's the one that actually is a positive, but I said it was an, or it's the, so I just wanted to throw out there, if you're like me, don't worry about it. You can be very successful, even if it takes you 3 minutes every time you see these formulas. Um, and then in the next note, I say there's all these different names, you know, false positive rate, true positive rate, true negative rate, one minus true negative rate equal. And so I do not think you need to memorize these terms. I don't think you need to know all these formulas in order to be successful. But you do need to understand the concept. Okay. So the way people pose problems, primarily the positive case is the one that they care about the most. So when you talk about a medical test for a disease, generally speaking, the positive case is you have the disease. And that's generally what people care about, because then it's like, oh, if you have this disease, we actually have this medicine that will cure it. I'll go and prescribe that. Okay. Um, but you need to understand what all of the issues are for your particular business case. So I would imagine that if you're doing self-driving, that it's possible that both false positives, thinking there's a school bus there when there isn't, and false negatives, not thinking there's a school bus there when there is, both of those could be really, really, really bad. Okay. So at the end of the day, you need to know your business problem. And you need to know what's the cost if I say there's no school bus there and there is, and the car just goes through and it runs over a bunch of children. Okay. What is the cost if there's no school bus there and I slam the brakes because I think there's a school bus and the car behind me hits me? Okay. So for any of these kinds of classification things, at the end of the day, we can talk about numbers and formulas and whatever, but as a good data scientist, you want to equate that to what does it mean to the business? And that's where it goes beyond just some, oh, I have 98% recall or whatever that means, right? Checking the chat for a second here. All right. Um, so having said that, for me, accuracy is something that's often reported, and I use it as a colloquial term when I'm writing uh, documentation for non-technical people. Okay. I generally don't use precision, recall, sensitivity, any of those other terms. I say we have a very accurate model. I might not actually literally mean accuracy, the technical term accuracy. It's just the English word that I find business stakeholders relate to. Um, but the flip side of that is you need to be careful if you are technical and you read my thing that's meant for non-technical people, that I will use the word accuracy in a very loose way where I don't literally mean the number of positives you got right and the number of negatives you got right out of everything. Okay. So most often what I see is precision and recall. Um, and this is when you care about the positive class and you don't really care about the negative class. Okay. So the example that was given to me years ago is you do a Google search. All right, things are changing now because we have right LLM guided search and you ask ChatGPT. But if you imagine just like a couple of years ago, old fashioned Google search, you do a search and what you see at the beginning is 10, let's say 10 top responses. Okay. Precision is how many of those 10 things are the thing that I wanted. Okay. That's generally speaking for Google searches, what people care about most. Is if you do a search for, I don't know, whatever, carpenters in San Diego, you don't want to see a carpenter in New York and you don't want to see a plumber in San Diego. You just want to see carpenters in San Diego. Okay. Recall would be what fraction of all of the carpenters in San Diego did you return to me? And depending on how you measure it, you would have to keep going through, multiple pages of whatever. But so you can see that in this case, you don't, in a Google search, you don't really care about the infinite number of things that are not carpenters in San Diego. You really just care about the positive class. And that's why people use precision and recall for these kinds of problems. In medicine, I see sensitivity and specificity talked about as the two most frequent metrics. Sensitivity is the same thing as recall. And so this is, if you've got the disease, what are the odds the test is right? And that it tells you have the disease. So you would like that to be really high so that you can correctly identify the people. If it's contagious, you don't want them to not know they have it and have it spread or whatever. But specificity is the reverse, which is I can make a test very high sensitivity by just saying everybody's sick. But the cost of that in medicine is that we're now spending money on treating people who don't need the medicine. And on top of that, they're going to have potential side effects. Or if it's not medicine, if it's surgery, then there's, other bigger side effects that you could have in terms of lifestyle and even, a very small chance that somebody could, die because of surgery or something like that. So I put a link to Wikipedia has a page that has 80 jillion formulas for different things. If you see a different one, you can look it up. But these are not the only ones you'll see, but these are the top ones: precision, recall, and sensitivity and specificity. Okay. And again, it depends on if you have something where you really only care about the positives, that's one thing. In medicine, you tend to care about the positive and the negatives. If you had something that was, I don't know if I can come up with an example, but it's like if somebody finds out that if you have a common cold and you just eat an orange, it'll cure the cold within 12 hours. Okay. And there's very few side effects from eating an orange. You don't really need to worry about the specificity because there's few negative, there's the false positives. There's few bad outcomes from prescribing somebody to eat an orange. It's inexpensive and there's no side effects. So that'd be a case where you don't. Okay. So anyway, that's just me kind of going a little bit deeper in terms of like not repeating what the author says about the metrics, but about why people use different metrics and why you should care about them. Any other questions on the metrics? This is the heart of the chapter, so feel free. We should go deep if people have questions. All right. In the next section, I've kind of foreshadowed a little bit, but goes into more detail about precision and recall. And there's an important point that if you look at F1, which I find a lot of beginner books and whatnot will talk about F1 score. And one of the things they'll talk about is this is a way in which you can have one number instead of having to worry about two numbers: precision and recall, sensitivity and specificity. And in particular, an algorithm can only optimize one number. It can't optimize two numbers. So F1 is attractive. It has this nice property of it's this one number. And so I like the fact that the author makes a point that F1 is going to, if you optimize that, is going to seek something where the precision and the recall are similar. All right. And depending on your use case, that's not necessarily what you want. So if you have some disease that you're able to treat and the treatment costs 50 cents, but failing to treat the disease could cause the person to have massive problems for life. And if giving the medicine to someone who doesn't have the disease has very few side effects, then you don't really want that even point. Okay. If the false positive cost is very, very low and the false negative cost is high, then what you want is really high recall. So you don't want the best F1. You want it swung way over. You're okay with a little bit of loss of precision because let's say you prescribed it to twice as many people that then actually needed it. That means that half of the people are going to pay 50 cents and there's no side effects. But if you miss one person, then they could be whatever, lose an arm, like, you know. So you should understand that F1 is written about kind of like it's a solution, but it's I caution against really paying too much attention to F1. I'll also mention that there are variations of F1. So you may see there's F beta, and what you can do is you can use a constant to shift the balance between how important precision is and how important recall is. And so you can, if you have a problem that doesn't want equally precision and recall, you can use this with a different value in order to tilt things. So even if you have something where there's a not equal, that is an option. But generally speaking, what I say to people is if you're trying to understand the problem, don't worry, go ahead and use more than one metric. We see this chart, figure 3.5, where the threshold is on the x-axis, and then you can see precision and recall. And so as you set the threshold higher, then that means fewer and fewer things will be positives. So your recall goes down. But hopefully, if you have a good model, that higher threshold means that you're more sure and you're going to be more often right about the ones that are positives. And then the reverse for lower threshold. The one thing I want to caution you, though, is that the shapes of these curves, you should not trust that too much. Okay. If I took all of the predictions of this model and for everything below 0, I multiplied it by 10. Okay. So whatever, this negative 20,000 becomes negative 200,000. But for everything above 0, I left it the same. Then basically what would happen is this chart would get stretched out and it would make the right-hand side of this chart look much more squished, and it would make these slopes look much steeper. Okay. If I manage to sort of widen the spread of everything between negative 20 and positive 20,000, if I kind of took those and I spread them out so that they were between negative 200,000 and positive 200,000, then I could make these slopes look very flat and not very steep or whatever. So this shape is something that you should not completely trust. So if you have one model and you say, oh, look, the curve is much steeper, that really depends on your scale. And so you can't just completely trust based on the shape of this graph. Yeah, question? It's really not about they're more accentuated on one side or the other. It's just that these thresholds are not calibrated. Okay. And so in the extreme, if all the positive numbers were between 0 and 1 and all the negative ones were between 0 and negative 5 billion, then this thing would look really steep because I'd have to draw the graph from negative 5 billion, up to 1, but the whole positive part would only just be one tiny sliver of it. And so then these lines would look super steep. And if you scaled the numbers other ways, then you can make it look a lot flatter. All right. I'm not saying don't ever look at this chart, but you just have to understand that your x-axis here, these thresholds are not calibrated. And so if I have two models, and this model, you can see you have a lot of values between negative 40,000 and positive 40,000. If I just train another model that's no better, but the predictions were between negative 20 and positive 20 instead of 40 and 40, the whole thing would look more squished. But it would be an identical model. But you look at the curves, the curve's a lot steeper. So that's all I'm saying. Is you have to be very careful because this x-axis is not calibrated. Yeah. That's an awesome question. So the question is it a matter of calibration or imagine a matter of scale? So if you got all the values between 0 and 1, you still couldn't compare shapes because it's not just scale, it's actual calibration. And so if between 0 and 1, I had a lot of predictions that were just between 0.48 and between 0.52, then I have this massive steep line. But if instead my predictions were at point not, you know, 0.05 and 0.95, then you'd see like a much more gradual. So ultimately, if you really wanted to, instead of having on the x-axis your raw predictions, you could convert them to percentiles. And you could say the bottom 5% of predictions, the bottom 10% of predictions, the bottom quarter, the midpoint, the median of my predictions, and so on and so forth. And that would be a way to have sort of apples to apples from two different models. Okay. Because then it doesn't matter what the value is. You're just simply saying for the exact same validation set, my median is the middle prediction, no matter what model I'm using, and the top quartile, and so on and so forth. Okay. And that's actually how people, that's a simple way that people calibrate models so that they can be compared. But more simply, I will note that if instead of drawing it that way, you do a PR curve where you have precision and recall on the axes instead of threshold, this curve does not change. So if I just take all the numbers and I multiply them by 2, the curve doesn't change at all. All right. So there's a lot of charts you can look at, and we covered 2 of them here. But the main thing I want to say, the caution is whatever chart you're looking at, understand, is it something that is affected by calibration, or is this a chart that is calibration independent? And off the top of my head, the ROC curve we're going to talk about next and the PR curve are the 2 that are not affected by calibration. But almost any other chart you look at is going to depend on, does my output have a lot of 0.6s or do my model have a lot of 0.9s? And it's not better to have 0.6s or 0.9s. What you really want to know is, are the 0.6s correct? Are the 0.9s correct, regardless of their actual raw value? I'll just also comment that doing a lot of training with neural networks, the longer you train them, the more the values tend to get pushed to the extremes. So if you just have something that's doing binary classification and you train it for a really long time, then you tend to have a lot of 0.001s and a lot of 0.999s. And they're not actually any better than when they were 0.6s and 0.4s. They just, in terms of raw value, tend to creep towards the ends because that's a way of lowering the loss. But they're not actually better. They just look closer to the ends. All right. So the PR curve I found early on took me a little while to get used to reading this. What you can't see on here, the very property that makes it calibration independent is you can't see like what threshold actually causes any of these particular points on the PR curve. All right. But the idea is that if you have very low thresholds, you don't know what they are exactly, but then your recall will approach 100% because you're basically saying everything is a positive. All right. But generally speaking, what happens is your precision goes down. And then if you go the other way and you set a very high threshold, then your recall drops towards 0 because now you're not calling anything a positive, but your precision can go higher. And depending on your particular problem, so lately I've been working on a bunch of problems where we're really focused on recall. We don't want to miss things. Okay. So I'm kind of focused on what's the shape of the curve in the lower right corner. And the steeper it is up here, the better. If you're really worried about precision, then that's actually a little bit harder because you can see that in this corner, it's how do I say, the The shape in the lower right corner is very simple. It just kind of goes down into the corner. It's a question of how steep. Here you have this phenomenon where the line gets a little wiggly, bumpy, and it also has this drop here. And so it's a little bit harder. But basically, I don't think I'm explaining this very well, but with a little bit of time, you can get used to reading these PR curves. Yes. Yeah. Yeah, that's exactly right. So I work for a security company, and so if I miss someone who breaks into a house and steals a bunch of things, the cost of that is very high. If I occasionally say, "Hey, the security guard should take a look at this person walking by," but it's a perfectly innocent person walking by, the cost of that is whatever, $1 of somebody's time to look at that. So that's an example where the false positives and the false negatives have very, very different costs. Um, and so a lot of the things that I do are very tilted towards the recall side. Yeah. Yeah, the question is why does it kind of go down here? There's a note in the book, a footnote that says if you look at the recall curve, you'll notice that it's really nice and smooth and monotonic. Okay. But the precision curve has this weird jaggy stuff over here. All right. Um, if you think about all of the predictions, so the reason why it gets jaggy here is because um, uh, if you look at your predictions that have very high scores that you think are positives, but some of them are wrong, then obviously if you move your threshold from to the left of a wrong one to the right of a wrong one, then your precision goes up because you just everything is the same, but you just threw away one bad prediction. Okay, it's not necessarily a bad thing if you move it to the right of a correct prediction. But basically, what you're doing is you're taking one out of the denominator and you're taking one out of the numerator. And in fact, your precision goes down. So if you were, say, 9 out of 10 correct and you go 8 out of 9, 8 out of 9 is actually a lower number than 9 out of 10. Okay. If the tippy top most, the prediction you have with the highest value is wrong, then you will not hit that upper left corner because no matter how high you raise your threshold, you'll never get to 100% precision. If your topmost ones are correct, then you can actually see it go up to 100% in the upper left corner. Does that answer your question? Cool. All right, let me double check the chat. There's a couple of messages here. Are there techniques to auto select the balance between precision and recall? Um, yes and no. So basically, if you decide how important they are, so if they're equally important, then you can use regular F1 and you can just pick the one that's the highest F1. If they're not equally important, you can use the weighted F1, the F beta. And again, you can just pick the one that has the highest. Uh, so if necessary, if you had some high volume situation, absolutely you can automate that. For low volume, I tend to just look at it and I think about it a little bit more in that way. Uh, hmm, great. Thanks for the additional color in the chat. New message. Cool. All right. Any other question about precision recall and PR curves? All right. Um, So the book mentions that the PR curve tends to be used more heavily for classification problems where the positive class is rare. And one of the reasons for this is because the ROC curve is looking at, so just so you know, it took me a little while to get used to the ROC curve as well. But basically, it's, I should actually flip over to it if I can. Where did we have that? All right. So if you look at this curve here, you can see the y-axis is the true positive rate. So this is your recall, and over here is our false positive rate. The ROC curve always goes from the lower left corner to the upright corner. Unlike the PR curve, it always hits both of the corners. And the 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 way the ROC curve is calculated basically is you look at all the predictions, you sort the predictions by their value. Okay, so you can't have a model that just outputs true, false, A, B, 1, 0. You have to have a model that actually has individual values. Okay, and so you sort all of those, and then you basically just look at the cut points between all the values, and you say, if I set the threshold above the very first value so that I only have one prediction that I think is a negative and all the others are positives, then how much am I right and how much am I wrong? And then I keep doing this as I move. And so if you had a validation set that had 1,000 data points, you would end up having 1,000 points on your ROC curve, and then you just connect them with lines, so it looks like a nice smooth thing. If you have fewer data points, you'll see ROC curves where you can actually see the corners where you don't have a lot of data points and stuff gets connected. So it doesn't always look smooth. So like the PR curve, one of the things that's really great about this ROC curve is it's sorting all of your predictions, and it's just looking at the dividing point between each of your predictions. It doesn't care what the raw value of your predictions is. So this is something that's insensitive to calibration. It doesn't care if all of your predictions are 0.9s or all your predictions are 0.1s. It's just looking at the relative ordering. There's some rule for what you do when you have exact ties, and I don't remember what the rule is. I just run the code to produce the ROC curve, but technically speaking, you can have exact ties, and there's a proper way to handle them. So let's see here. What I'll say about interpreting the ROC curve, I'll say just a little bit. At the top end of your predictions, if you have a lot of predictions that are right at the tippy top end, okay, then what you will see is that this line in the upper right corner, instead of being very flat and close to the diagonal, will be very close to the top edge. Okay, and then the reverse is true for your predictions at the very low end. If you're very confident that it's negative, if those are mostly right, then this line will be very vertical. So if you had a very weak classifier that, even though it said it was more short, had a higher number, but it wasn't actually any more right than the middle ones, and even though it said, hey, I'm very confident it's a negative, but it wasn't really any more right, that's when you see something that's closer to this diagonal line. And in the extreme, if you just use a random number generator as your model, then you'll get this dotted line that's at the 45-degree angle. So depending on what you care about, again, this thing, you can't really tell. This ROC curve to me looks kind of symmetrical. Okay, they do not have to be symmetrical. It could be you have one that at the low end looks like this, where it's not very good. It has a lot of positive mixed in with its low predictions, but then it shoots up to the top here. And when it's sure that it's a positive, it's almost always right. So you can and you will have ones that are not symmetrical. Um, because it's kind of hard by eye to tell exactly what's, how close to the diagonal line, how far away from it is it. That's where you can calculate the area underneath this curve. And so one of the questions was about the rock AUC. So the area under this curve gives you an exact number. So if you have two curves that are close to each other and you're having trouble telling which one is actually higher, which is further to the upper left, you can just look at the number. And so if one says I have a rock AUC of 92, 0.92, and the other one says it's 0.93, then you know that the area for the second one, even though when you look at it by eye, you may have a little trouble telling which one is higher. So that's the primary use for AUCs, is to get a nice clear thing. Again, kind of like F1, I've seen rock AUC talked about a lot because it's a single number. And again, if your problem really cares about one or the other, if it's a Google search and you really care about precision, if it's some medical, like me, if it's a security thing and you really care about recall, then you should not choose the model that has the highest AUC. Because for your use case, you actually don't care about performance over the whole range of things. You're really more worried about the performance at the extreme. So I hope I did a decent job with talking a little bit more about the rock AUC. Any additional questions about the rock curve? Cool. Thanks for all the color, Ryan, in the chat. I'll just show. Can I? You guys don't see my screen, do you? So in the chat, Ryan was just showing here's a rock curve with fewer data points, and you can see it's very jaggy. You can actually see instead of it looking like a smooth curve. And this one I think is fairly clearly not symmetrical. All right. Moving on, multi-class classification. So they talk about the one versus the rest, one versus I don't even remember the one versus all. Anyway, the if your algorithm supports multiple classes, then you don't have to worry about this business, but you do need to know that for some of the ones that don't, you have to do this. Luckily, most algorithms do support multiple classes. Okay. So they gave an example of support vectors, which fundamentally is a binary thing. But most other things, if you have 10 classes, then it'll just output all 10 of them. And so then you don't have to worry about training multiple times and all this stuff underneath the hood. I made a note that the confusion matrix gets bigger when you have 10 classes, right? It's a 10 by 10 instead of a 2 by 2. And they show different ways that you can look at it. I just wanted to say, you don't have to feel like you should find the best one. It's okay to have more than one. It's okay to say, I wanted to see the raw counts for this reason, but I wanted to see the percentages for that reason. I wanted to see the overall percentages, but I also wanted to normalize it by row and see the percentages that way. So again, it's nice to have these rules of thumb, but you don't have to feel like there has to be the one right thing, just like there doesn't have to be the F1, the one metric or whatever. You can look at multiple things here. And I wanted to just check the whole group here. I'm not aware of any way to do the equivalent of a PR curve or a rock curve other than with two things. So you can just, if you have the 10 classes, you can just take two of them and you can plot a PR curve amongst just those two. And you can do this for different pairs of things, but I'm not aware of a nice way to just do it. So does anybody know of any charts, any like pretty ways to visualize multiple classes? All right. I'll monitor the chat and I'll come back if somebody put something in there. But yeah, I find the pictures very interpretable, and once you get to multi-class, it's just not as easy. So then we have multi-label and multi-output, and I find that these terms get really confusing. Um, so as far as I'm concerned, it's not super important to know the terminology. If you say, I have a classification problem with 10 classes, then the people who know the right terminology say, oh, yes, that's a multi-class problem. And if you say, I have a thing and I'm trying to label, you know, uh, I don't know, I'm totally blanking now, but um, in the book they have the contrived example of odd numbers and large numbers, and a number can be both large and odd, you know. um and so then that I guess is a multi-label problem. But if you don't know the name of it, it's not super important. There may be certain domains where you run into this. I don't i have not run into multi-label multi-output kinds of problems very often. um One other point, I think the author said something about um, when they were talking about the multi-output, and they were saying, oh, we're going to have 256 different values that we're predicting, and they're like, yeah, it kind of blurs the line. Is this a regression problem? Is this a classification problem? One of the things we'll see it as we get into the next, I would say, 3-4 chapters, is that some algorithms natively work with continuous numbers. And so we do tricks when we want classification. So logistic regression is a trick that takes just regular real numbers and converts it into a format where we can interpret it as either the positive class or the negative class. On the flip side, trees and support vector machines, they do splits. They cut things in half, and they are inherently discrete algorithms. And so when you have a tree algorithm and you're using it to predict a number, depending on how you do it, it may be that this tree algorithm only has 8 different numbers that it will ever predict. If you use like a simple decision tree, it's not really predicting continuous numbers. It's buckets. They're numbers. So if you just look at it at first blush, you may say, hey, this looks like a regression thing. But technically speaking, it's doing a classification thing. And it's just the buckets have numbers as their names. Um, so I think this is where understanding the algorithms, you can understand a little bit in terms of potential strengths and weaknesses. If you have a classification problem and your algorithm predicts numbers, that's usually not a problem. We convert numbers to classes, just like a number between 0 and 1. That usually works quite well. The reverse is not always great. So when you're using trees to predict numbers, there are ways you can help those algorithms because they fundamentally are not as good at being able to, you know, incrementally and infinitely give you different values. So that's one more note there. All right, I have 2 more notes from the exercises I just wanted to share. If you look at the Jupyter notebook that the author provided for exercise 1, which was how to get better results for MNIST. And he said, hint, you can use this K nearest neighbors classifier, which we haven't talked about. It's in like whatever, a chapter or 2 from now. But one of the things he does is he shows I can do a grid search on the hyperparameters for this algorithm, and I can find the best hyperparameters. But that would be really slow. And so he ended up using like 1/10 of the data and did his hyperparameter search, which is not guaranteed to be perfect. It's not guaranteed that you would get the exact same answers if you did in all of your data. But it ran so much faster. And so I wanted to point out that this is a very good pattern to follow. Okay. If you're working on a particular competition on Kaggle, if you're working on a particular problem, the number of iterations, the number of things you try is often the most important number. And so if you have to take a smaller set of your data in order to try new things, try more things, that's usually a good thing. And then once you say, wow, I tried a random forest and it stunk, it was terrible, but I tried whatever, light GBM and it was much, much better. Well, then you don't have to waste a whole lot of time trying to get perfect answers for random forest. You just see like, yeah, I'm not going back there at all. Okay. And then when you get to towards the end and you're sort of dialed in, now is when you're going to want to really hopefully have the resources to use all of your data and get much more precise measurements. But again, early on, when you're able to make big jumps, then if using a tenth of your data adds plus minus 2% to your score, but you're able to do something different and it jumps you up by 4%, then it doesn't really matter that plus minus 2%. You have a clear signal that this is something better. And so once you start getting to the point where you've gotten most of the value possible and your changes are producing smaller increments, that's when then you may need to say, hey, I need my cross validation, I need all my data, those kinds of things in order to get an accurate signal which way is uphill. And then my last note here is in exercise 2, he points out that sometimes when you're talking about your answer, not in terms of actually just building a model, you want to talk about the error rate instead of the accuracy. So if you say, in his case, he went from 97.1 to 97.6% accuracy. His accuracy went up 0.5%. Talk to a business person, and that's not really that impressive sounding. Like, oh, okay, it's 0.5%. But if instead you say my error rate was 2.9%, I dropped it to 2.4%. I cut mistakes by to 5/6 what they used to be. Like, oh, well, that's pretty good. You dropped, your again, assuming that you have some cost associated with those mispredictions, you drop that cost by 17%. People are on board with that. So I thought that was also a good thing, just in terms of, again, it's not really about the modeling, but about how you talk about it so that people can understand. All right. So we made it on time to the end of the chapter. I had one question that I thought of to just go a little bit deeper in terms of this chapter. The key message was metrics and how you understand what your model's doing. And we talked a little bit about validation and having more accurate metrics. But so in my scenario, I'm saying you've built a binary classifier and it's outputting prediction values between 0 and 1 for your positive class, 0 for your negative class. Can you think of a way to divide the predictions other than just simply setting a threshold and saying above and below the threshold? And then how might you measure the performance of the model using these divisions that might be more understandable to non-technical people? So said another way, really what I'm asking is, why might you want to take your predictions and divide them up into chunks and do metrics against those chunks instead of doing metrics against the entire set of predictions, against the entire output? Any thoughts? Yeah, please. Okay, so your data might not be uniformly distributed. That's a potential reason. Yeah. Another idea, or do we think the same thing? I'm sorry, I had a little trouble hearing. I think you said less computationally expensive. Okay, so yes, it would be less data to train on. What I'm getting at is I've trained my model and I have a validation set. And instead of measuring precision and recall my whole validation set, I'm dividing up my validation set into chunks for some reason. All right. I'll give you oh, yeah. Okay, yeah. So, what if the model's very sure some are positive, some are negative, and there's ambiguous ones in the middle? Yeah. So it might be that you say, here's the precision and recall when the model's really sure that it's a yes. Here's the precision and recall or reverse of it when the model's really sure it's a no. And here's what the precision recall looks like in the middle. So that tends to be something that for not again for business users, for non-technical users, sometimes if you just say like, oh, I have this whatever recall of 82, I don't know what that means. But if you say that like when it's really sure 10% of the time it's really sure and it's 99.5% right when it's really sure, but then in the middle we get to this region or whatever. So yes, so that's one reason. Another big reason is you often have problems where people aren't planning to use all of the predictions of your model. Okay. So if you're predicting churn and they say, I only have the bandwidth to call 10 customers and try to talk them out of canceling or to see how they're doing, maybe give them an offer, whatever, then you really only care about your top 10 predictions of your model. You don't really need to know how good is the precision and recall on that middle section order. So it's a variation of what you said in terms of the very sure. But in this case, it's not just so they understand it. It's because, yeah, in that case, they would be very worried about precision. They don't really care about recall, right? And because it's like, well, I'm going to call 10 people and try and get these customers to stay. If there are 20 customers who are potentially leaving, it doesn't really matter whether or not you got all 20 of them because they're only going to call 10 people, right? So this would be a case where you really are worried about the precision and recall of that top 10 or some variation. Okay. So again, just trying to go a little bit deeper and say that, yes, these are the standard ways you measure it. But at the end of the day, you have to understand the business problem and what is the value. And if the value is we're going to call 10 people and we're going to try and save them, if you are wrong in your predictions, then maybe they're going to offer discounts to people who would have stayed anyway, and the company's just going to lose money. If you're right, then obviously, they get to keep the customers and whatever that's worth, and so on and so forth. So understanding those, ultimately, it goes back to that step one of ask questions. How is this model going to be used? And so then you can turn your numeric metrics into actual company dollars. So if they say, oh, well, offering a coupon, like if it's a grocery store and you offer $5 coupon, that doesn't really hurt the company that much. Fine. But in other cases, it might be like, yeah, actually, this is a big discount and we don't want to offer it unless we really need to. But if we can save a customer, then it'll be worth it. All right. So that's all the notes that I had on the chapter, the extra prepared material. Any final questions before we wrap up here? All right. Awesome. Thanks, everyone.